Okay, welcome back to the class. So today we are studying the chain rule. So the composite function f of x is f composite g, or f not g right here. F, we call it composite g, applied to x, which is f of g of x. Okay? We would like to compute the derivative of x with respect to variable x, f with respect to x. So the chain rule tells us that f prime of x here, or df over dx, is the derivative of f of g, right, applied to x, because capital F is f composite g, and the general tells us that it is f prime, and here f is a function of g of x, sorry, times g prime of x. So this is the chain rule. So we see that here, in order to take the derivative of g, what we need is it should be differentiable at x, right? In order to take the derivative of this, it should be differentiable. So it means that g is differentiable at x. That is the condition. Similarly, in order to take the derivative of f, so f should be differentiable at g of x, right? It makes sense when we look at this. So that is the condition. Or we can write it in Leibniz notation. So if y is the function f of u, and u is a function of g of x, right? Another way to write it. Then y would be f of u, and u, we know that it is g of x, right? Another way to write it. Or it is f composite g applied to x. They're the same thing. I'm sorry? Leibniz, the name of a mathematician. Leibniz notation is a very famous mathematician, and he suggests an idea like this. He writes this way, so we call it just a name. So now, from this notation, dy over dx, which is the derivative of y with respect to x, will be the derivative with respect to u, dy over du, times du over dx. It is easier to memorize, right? Somehow imagine du and du cancel each other. Imagine. But it is not a fixed thing, so we just let it be this way. So these are the chain rule. Oops. So this one or this one, they are the same thing. Now let us go to an example. Given a function f of x is square root of 2x plus 1. Do you remember? We need to compute a prime. Let us call it capital F here. So we need to compute f prime. So in Leibniz notation, y will be square root of u, where u of x is 2x plus 1, right? Is that okay? Are you comfortable if I write it? Okay, then what we need to do is to compute. So imagine y here is capital F of x. If we write it this way, f of u, which is square root of u, right? And then we need to compute f prime of x, which is dy over dx, right? And from the notation, we know that, what is it, Drake? Yes. And? Perfect. Okay, it means that we need to compute the derivative of square root of u, right? D over du of square root of u times du over dx. It means that d over dx of 2x plus 1, right? Look at this. This is square root of u, which means that it is u to the 1/2, right? And here, what is d of 2x plus 1 over dx? Lexi, can you help me with this one? Yeah, d over dx of 2x plus 1. Oh, what is it? Just 2. Right? Because here, the derivative of 2x gives us 2 times x prime. X prime is 1. Then finally, it becomes 2 right here, right? And here, u to the 1/2 and d over du is similar to the variable x, right? It will be the power of this, it is 1/2. And u to the 1/2 subtract 1, right? And the number 2, we just rewrite it here. But here, 1/2 minus 1 is negative 1/2, right? So it will be, and the number 2 here cancel with 1/2, right? 1/2 times 2. Therefore, finally, it will be u to the negative 1/2. And remember, u here, we can write it. The negative here, we can push it down to the denominator, and it becomes u to the 1/2, right? And to the 1/2 is square root of u, right? And u is 2x plus 1. So finally, we have this, okay? Do you have any question about the first example? Very good. And now, that is one way. Another way, if we think about this. So we know that capital F of x is square root of 2x plus 1, right? So the function f of x, if we define it, let us call it f of u. Is square root of u. And g of x is 2x plus 1. Right? If we define these two, then we know that capital F of x is f composite g, then apply to x, right? It means that it is f of g of x, right? If you want to double check it, let us write it clear. And we see that g of x is 2x plus 1, right? So f of 2x plus 1. Now the input is 2x plus 1. The output should be square root of the input. Yeah, it makes sense. It is capital F of x, right? They are the same thing. Then apply the chain rule. It says that f prime of x is f prime of g of x times g prime of x, right? From the rule, just rewrite it. Now here, it means that we need to compute derivative of g of x, which is square root of u, right? Okay. And g of x, the similar story, which is 2x plus 1 prime and similarly, square root of u, it means u to the 1/2. Take the derivative of that, give us 1/2 u to the 1/2 minus 1. And g prime here give us 2, right? And finally, we do the similar things. Finally, we have 1 over square root of 2x plus 1. So is it clear? You have any question? Gary? Is it clear, Gary? Yes, U is a variable. If we treat it here, U f prime, it means small f prime here, it means derivative d over du of square root of u, right? Just another, it's similar to d over dx of square root of x. They are the same thing. Just we use a different notation. It's just a name we assign to a variable, right? Is that okay? Are we good? How about people on Zoom? Matthew and Michael? Are you here? Okay. Now, let us play with another one. In this case, a remark. dy over du, where y is square root of u, it is 1 over 2 square root of u and dy over dx is capital F prime, and this is the final result, 1 over square root of 2x plus 1. They are totally different. dy over du and dy over dx are two things, okay? Don't be confused. Are we good? Then let us move on to another one. Okay. Thank you for people on Zoom replying to me. Actually, you are required to follow, actively follow, but I don't want to feel pressure here too much, but please pay attention. Okay. Suppose we have the function f of x, which is 2/3 of square root of x cubed. We need to find f prime. Okay, now let us do it. F prime is d over dx, right? Which means d over dx of this function, 2 over 3. And from definition of root function, radical sign here, it means that it is x to the 3 and then raised to the power 1/2. The radical sign is something to the 1/2, right? And here, look at this. Look at this number, 2 squared and then to the 3. What is it?
2 to the 6.
Very good. 2 to the 6, or we can write it in details. 2 square times 2 square times 2 square, right? Because this 2 to the 3 will be itself multiplied 3 times. 1, 2, 3. And we know that it is 2 to the 6, which is also 2 to the 3 times 2. So from this simple one, we know that the power rule tells us 2 squared and raised to the power something, it will be the product of these two powers. So we have this, right? So from now on, when you don't remember a rule, try to play with some simple example to recover it, okay? So now it applies here. X cubed times 1/2, which is, it means that we just continue from here. It is d over dx of 2 over 3 and x to the 3 over 2, right? Now, it is x to a number. The derivative of this will be the constant, we can take it out. And then derivative of x 3 to the 2, we bring it down here, times x to the 3 over 2 minus 1, okay? Then we see that 2/3 over 3 over 2, they will cancel each other. And here, x to the, this one, it is x to the 1/2, right? Which is square root of x, okay? Okay, let me remind you about the domain of this one. We see that the domain of this is the things under the radical sign should be positive. It means x cubed should be positive, which implied x should be positive. This is the domain, okay? So now, this is the way we study in section 3.1 about the rule of polynomials. But now we can apply the chain rule, okay? So now if we say that y is square root of 2 over 3 of square root of x cubed, now if we say y is equal to 2 over 3 square root of u, right? And u in this case is x cubed. Okay? Now the chain rule. Okay? We need to compute df over dx, which is d over dx. F in this case is y. It is the same as dy over dx. Yassini, can you help me? Dy over dx. So what is the chain rule in this case? So dy over du and then du over dx, right? Memorize this rule, okay? It's somehow like insert the du in the denominator here and numerator here, imagine, okay? Now, dy over du, and in this case, it will be d over du of 2/3 of the functions use square root of u, right? Times du over dx, and u in this case is x cubed. Okay, is it clear? William, can you see it? Very good. So now, again, d over du and 2/3. Square root of u is u to the 1/2, right? And here, du over dx, what is it, Daily? Du over dx of x cubed? Yes, perfect. 3x squared. Very good. So now, again, d over du of this one will be, okay, the power here, we will bring it down, it will, and the constant, we can take it out here, 1 over 1/2, and u to the 1/2 minus 1, right? And 3x squared, we just rewrite it. Okay. The product of these constants, they 2 here will cancel with 2 here, 3 here will cancel with 3 in the denominator here. So the constant cancel each other. Okay, and u to the 1/2 minus 1 is, what is it, Andre? Perfect. It is u to the negative 1/2, negative 1/2, right? 1/2 minus 1. Then here is x squared, we just rewrite it. Again, the negative power from the numerator, imagine the whole number, it means that that whole number is divided by 1. They're the same thing. Now we push it down to the denominator. So the power from negative here, it will be changed to the positive power, okay? And x squared, we just rewrite it. And again, it is 1 over square root of u, and u in this case is x cubed, right? Now put everything into this times x squared, okay? Interesting. Now, we need to simplify it, right? Because this is a same formula. And previously we found that derivative of this finally would be square root of x, right? And now applying chain rule, we will end up with this. Now let us simplify it. How can we do it? Imagine x squared is x divided by 1, right? Therefore, the product of two fractions, it is the same as x squared divided by square root of x cubed. There are many ways to write it, okay? How can we simplify it?
We can turn the square root of x cubed into x to the root.
Yes. Oh, yeah, it is faster. Yes, very good. Okay, it is even faster. Okay, if we write it this way, x to the 3 over 2, right? It's faster. Okay, very good. This is a good way. So they have the same base. Base x here. The product rule tells us that it would be the base to the difference of the 2 power, 2 minus 3 over 2. Okay? Which is? Yes, x to the 1/2. Very good. or square root of x, they're the same with the previous result, right? So, are we good? Okay, just do it slowly, you get the result. These problems are not difficult. So now let us study some general cases. Okay. If y is sine u and u is differentiable function of x, okay? It means that u is a function of x, okay? So the chain rule tells us what? Dy over dx is dy over du and du over dx, right? And dy over du, what is it? Y is this guy, right? Yes. It would be cosine of u and then multiply with du over dx, which is u prime, right? So the chain rule for cosine function of u. Similarly, if y is cosine of u and u is a function of x, then the chain rule tells us that dy over dx will be dy over du over dx, which is very good. So derivative of cosine gives us negative sine of u and then du over dx, which is also u prime. They're the same thing. Okay. That is the second case. Another case. So how about if u is a polynomial? So y is u to the n. U is a function of x. So what is dy over dx? The same rule, dy over du, du over dx, right? And dy over du, and y is u to the n. Du over dx is simply u prime. Okay? So, what is it? Justin, can you turn on your camera and tell me what du is in this case? Justin, can you hear me? about Kendall? Can you hear me? Okay, very good, Morgan. Okay, so d over du of u to the n, so u is a variable, from power rule tell us that, okay, derivative of this polynomial give us the number n here, u to the n minus 1 times, okay, u prime here. So this is another case, right? For example, we want to compute derivative of y, which is x squared minus 1 to the 10. Find u prime, y prime. Okay? In this case, if we say y is u to the 10, right? And we know that u is x squared minus 1, right? So the general tell us that dy over dx, what is it? Log in. What is dy over dx? The general. Log in again. Can you hear me? Andre, can you help him? Yes. Yes. So very good. The general is always like this. And here, dy over du is d over du of u to the 10, right? And d over dx of u, and u in this case is x squared minus 1. Okay? And again, it becomes simpler. So, Yassini, what do we have here? d over du of u to the 10. Yes, perfect. It will be 10 u to the 9 and multiply with d over dx of x squared minus 1. Very good. It is 2x here, right? And again, u, we know that it is x squared minus 1. So we write everything in terms of x. We have 10 times x squared minus 1 to the 9 times 2x, right? So we simplify it, make it better. 10 times 2 give us 20. And x here, we can put it in front of this. And x squared minus 1 to the 9, we just rewrite it. So now, is it clear? Okay, very good. Okay, now let me remind you the exponential function and logarithm function. If you want, you should go back to review it. So you can find it in the math website of our department, Math 1021, section 5. It is very clear and details. So there are a lot of things there, very useful. But for now, let me just exponential function. Exponential function is a function y is defined as a to the x, where we are interested in the value of y of a is positive. We care about why it's positive. And you see that 1 to the anything will be 1, right? So it's not very interesting. So we don't care about that. So we also exclude a is 1. This function we call exponential function. And the very important properties is that it is one-to-one function. Then this function, if it is one-to-one, then there's an inverse of this. So and the inverse of exponential function is the logarithmic function. Okay? Logarithmic function is the function y is log base b of x, which is defined as equivalent to. So this is the base, right? The base raised to the power of this value, which is equal to, say, x is b to the 1, right? And we also care about the base where b is positive and b is different from 1. That is these number we care about this, right? And because b is positive and it is a positive number, raised to any numbers, right? It will always be positive, right? That is why and x is equal to a positive number. Therefore, x is always positive. Right? Larger than 0. Right. Okay. Now, from this definition, we know that, okay, look at this. We define logarithmic base, log base e of a number b, which is like this. We can write it this way. If the base is the number e, the constant, then we write it ln b. And from the definition, right? What does it mean? We can write it b will be e to the right hand side here, right? The same as here. See? E to the L N X. Okay? Okay, these are basic things of exponential function and logarithmic function. That will help us to compute the derivative of any function y, which is b to the x. And we need to find the derivative of y with respect to x, right? Remember, this one, it is not. Can we write it? Y prime equal to x and b to the x minus 1? It is. It is not. Be careful. So from this is wrong, right? So we need to apply the chain rule to find this derivative. Okay? Is it clear? So we cannot simply compute it like the polynomial. Okay? So now, how can we find dy over dx, which is in this case is d over dx of b to the x, right? Okay? And we know that from here, b, we can write it e to the ln x. Let us substitute here and see what happens. So it is the same as e to the ln x. Ln, oh, I'm sorry, here should be b, right? The number b, not x, sorry. Yeah, raised to this power. Something sometimes we write, we think one way but write differently. So b is e to the ln b. Therefore, b to the x will be e to the ln b to the x. And this is the power rule we just discussed, right? Then it would be e to the what? Torrington? To the power something, and then raised to the power of x, right? To the, yes, ln b times x, right? It will be the product of the two powers. Very good. Then here, look at this. If you imagine it is e to the u, right? Or we are computing, sorry, d over dx. We are computing the derivative of this guy. Okay? Then the general imagine here is u of x, e to the u, where u, it is equal to e. We are computing d over dx of e to the u of x, right? Where u of x is ln b times x, right? The same thing. But now, when we see it this way, we can apply the chain rule. Okay? We good? So, William, from here, so what does the chain rule tell us here? This is u. William? So here, e to the u, right? That is a function. So it would be d over du of e to the u, right? And then the chain rule tells us that du over dx here, okay? This is from chain rule. And the exponential function d over du of e to the u, what is it?
E to the u.
Yes, e to the u and u prime here, right? U prime, so you see that ln of b simply a number, right? B is a number, ln of b is another number. A number times x, so take the derivative, it gives us this number, right? Which means it is e to the u, where u is ln b times x, and then times ln b, right? Okay, from now, this again, e to the ln b, which give us, what is it? We can write it this way, right? Ln x and the ln b times x, it means e to the ln b and then raised to the x. And again, e to the ln b is, what is it? Okay, we just written this before. This is b. E to the ln b is b, and then b to the x, ln b. So finally, it tells us that, okay, d over dx of b to the x will be b to the x times ln b for any numbers b larger than 0 and b is not 1. Okay, I think we can stop here and see you next week. See you everyone.